with our lecture number 2. Okay, in the previous lecture, we have some discussion on the introduction of electrostate, like how electrostate came in picture and what are some basic things we have to follow and we should know. Like with the definition part and with some questions, we have learned something. Okay, so now in lecture 2, we'll study about Gauss law and its applications. And the most important one, electric dipole. Actually, dipole is an important topic in CSIR NET GRF paper and GET 2 because many types of question can be formed by this topic, electric dipole, and work due to a dipole, work, energy, etc. So this is important topic, and that is why we will read these topics today. So be attentive in today's class. The class is quite important with the aspect of the exam. Okay, so we'll start with Gauss law. So, guys, now you know about electric flux. We have already discussed about this. So, electric flux is basically the field lines coming out of per unit area. So, if we put a frame, let me select some pointer. Okay, if we put a plane of area A in mid between the field lines or the electric field, so the the number of counts we are getting within this area of electric field lines is called electric flux. So basically the mathematical formula was phi equals to E dot A, where A is area, is the magnitude of electric field, and this dot product is becoming cos theta here. So phi equals to EA cos theta. Now, if I am changing the positions of that frame, then how can the flux is we can get the flux in different ways. So if the plane is like this, we are getting phi equals to E dot A. If the plane is normal to the surface, means perpendicular to the surface, then the area is same. The plane is the same, the this loop is the same, and hence the area is also same, but we will get flux now different answer of flux we will get. Why? Because we are just changing the position. So flux also depends on the relative orientation of field of the surface. Okay, and obviously flux is depending on orientation. So if the plane now is making some angle theta with these electric field lines, so we are getting different results. And okay, this one is A cos theta for this line, and this is the area. It is inclined over angle theta. Now it is again inclined over theta, and the value of theta is increased. So we will get different results, obviously. Okay, so what you guys have to do here, just calculate the flux of the electric field to this surface of A. Here is a frame of area A, and there are three cases, A, B, and C. You can see on your screen, and you have to tell me what will be the flux. So what will be the flux in this case A? Anyone? Fast, please tell me what will be the phi for A.
E into A, because cos theta is 1.
Yes, right, E into A. For B, what we are getting for B?
0, because 90 is 1.
Yes,
0.
very good. And for C again?
EA cos theta. It
Good,
depends
very
on
good.
the...
Very good. So these are the three conditions, these are the three orientations, and we are getting the different results. Hence, we can conclude that the flux also depends upon the orientation of the surface. Okay. What if surface is curved? like we have any surface which is not flattened, it is having some curve like this. So now is there any chance to the variation of flux? Yes, there are equal chances, and in this case and for the different geometries, what we do, we just calculate the small area flux, like we will calculate the flux d5 for this small area dA, and then we will integrate over the whole surface. Okay, we will do this thing for the different geometries of any surface. And in the case of a closed sphere, if we have any closed sphere like conducting shell, like a plane, like a cube, like or anything. So in the case of a closed sphere, what we will do? We will do the integration over all the infinitesimal values of flux d phi over a closed surface. Okay. So, if we have any spherical surface and there is a point charge at the center of that surface, then what will be the flux coming out of this surface? So, flux of electric field is used to be integral of d phi, which is equals to E dot dA. Because of that dot product, we are getting E dA cos theta. We can write E as 1 upon 4 pi epsilon naught Q over R square because the charge is Q. So we are putting this plus Q. And the radius of sphere we are considering small r into dA. So this K into Q means 1 upon 4 pi epsilon naught into Q is a constant. So it will come out of this integration. So in the integration, there will be only dA over R square left. So what is this dA over R square? dA over R square is the infinitesimal area because dA is the small area and R is the radius comparatively much more bigger to this dA. So this dA over R square we will define as d omega. What is this d omega? D omega is a solid angle. How can we understand a solid angle? If you have seen any watermelon, so just we have to cut that watermelon into 8 equal pieces. So what we will do, we will just cut it half first, then we will cut the half part of each half one, and then again. So we can do those 8 pieces. So if I am considering any one piece of that watermelon and I am having that one piece at the same place where it was in the watermelon, and I am watching that center of that one piece, that 1 by 8th area, or that one piece, that center will make an angle d omega. So that is the angle d omega, that is called solid angles, which is only the full fulfilled geometries like the sphere, like the symmetrical geometry, sphere or shell. So we can have this d omega as d over r square. So we can put this d omega here. And this d omega has the maximum value of 4 pi. So we are getting at last phi equals to q over epsilon naught. That is our Gauss law. So hence we are deriving the Gauss law from flux of electric field. Okay. So now you guys know that what is a Gauss law. Let me ask you one question, and you will answer me. What do you think about that situation? There is a situation, you are traveling in your car, and somehow the weather is not good. It is raining outside, and suddenly thundering starts. So the electricity is falling from sky, and there is no shelter, no homes. There is only forest everywhere. There are only trees and a road going through this that forest, that thick forest. So what will you do to save your and your family's life? What will you do? What do you think you should do?
Then stay into the car.
Why you will stay into the car?
We learn into disaster management. That's
What?
all that
Why you?
car. Inside the car is a register of electricity.
Ma'am, the car provides electrostatic shielding.
Yes, Justin. Okay, so yes, Hasmukh, we will stay in the car. That is the only way we can be safe. And Justin is right. We will apply here Gauss law. So this is the good example of explaining Gauss law. Like the car is made of any metal, like steel or iron. So that is a metallic shell, a hollow metallic shell, and that will be a closed surface if we will put our mirrors down, and if we are staying into the car, and if electricity falls upon the car, none of the electron, not even one electron, can enter in the car and harm your body, because all the current will go through the surface, and by the way of tire it will go into the earth, and earth is a good conductor, so it will absorb all the electricity inside, and hence you are safe. So that is a good application of Gauss law. So now you guys know the daily life application too. So just we will do some theoretical applications. So there is a symmetrical diagram you can see on your screen, and there are four surfaces A, B, C, and D, and the distribution of charges is like which is in the diagram. So if we want to calculate for surface A the flux for this whole surface A, so what will be that phi A? What you guys will do, you will add those charges who are situated inside that surface only. So you have to just add them and conclude them for a phi A. And for surface A, what will be phi A? Anyone? It is easy question, guys. Please
Then
answer.
charge is plus 2q.
What?
Charge is plus 2q.
Charges plus,
Value of charge is plus
yes.
2q.
So we have to sum up all the values of charges. So plus 2q plus q is 3q minus q. So we are getting 2q over epsilon naught. So phi A will be, what will be phi A? Because we are here applying Gauss law, which is phi equals to q upon epsilon naught. So we are getting this phi A equals to 2q upon epsilon naught. And hence, what will be phi B? For the surface B, for this surface, there are only two charges bounded, minus q and plus q. So q over epsilon. So phi B will be q over epsilon, and so on. You can now calculate phi C and phi D. So it is easy. We have to apply here Gauss law. If area and electric field is given, then calculate from that formula phi equals to E dot A. And if area and electric field is not given, then calculate by Gauss law. Okay, so now we have to calculate the electric field produced by a point charge using Gauss law. So here is a point charge. Here is a point charge plus Q. And you know that for a positive charge, the electric field lines usually come out of that charge. So for an infinitesimal area dA, what we will do, we will just calculate that electric field as we were doing earlier. So we will get various values for different thetas. Like we have electric field for point charge like kq over r square, na? So we will just uh, multiply that value into that area in which that charge is situated. Okay, so we are doing the same. E dot dA equals to q upon epsilon naught. E dot dA is outside and the integral will be of dA. dA means the area. Area is, if we are considering a point charge, then we will have a conventional closed surface which will be a spherical surface. So 4 pi r square. So that EA equals to E into 4 pi r square equals to Q over epsilon naught, and we are getting E equals to 1 upon 4 pi epsilon naught Q upon r square. So which is similar to the Coulomb's law. You can see that this E equals to 1 upon 4 pi epsilon naught Q over r square. We can also derive using Coulomb's law. So is this the result that we can conclude that Coulomb's law and Gauss law are similar? Can we say that Coulomb's law and Gauss law are similar? No, we can't say that. So can we say that Gauss law is more fundamental than Coulomb's law? Some result should be there, na? So is Gauss law more fundamental or more important than Coulomb's law? But it is not like that. Both the laws have same importance in electrostate. Both the laws are different, but Gauss law have some limits and Coulomb's law have no limits. What are the limitations of Gauss law? Gauss law have the most significant limit, that is it can only be applied on closed surfaces only. So some very symmetric problems can be solved using Gauss law, but there is no such limitation on Coulomb's law. So no, Gauss law is not more fundamental than Coulomb's law. Okay, so this is your Gauss law. The total flux within a closed surface y equals to closed integral E dot dA, which is equal to Q enclosed over epsilon naught. Epsilon naught, the value of epsilon naught you always know. So some very certain problems with a great symmetry can be solved using this law, and those special symmetries are spherical symmetries, which we will form for point or sphere. Cylindrical symmetry we will form for a line or cylinder. Planar symmetry we will form for a plane or sheet. The spherical symmetry has the charge density depending only on radial distance from central points. Cylindrical is depends only on perpendicular distance from line, and planar is depends only on perpendicular distance from plane. And the Gaussian surface is spherical centered at point of symmetry. For cylindrical it is cylindrical. For planar it is pillbox. Okay, so just underline this thing. For planar it is pillbox or cylindrical with axis perpendicular to plane. Electric field is perpendicular to A minus cos theta, which is equal to 1. It is E perpendicular to A, and it is also E perpendicular to A. When we will do some examples, we will came to know how this electric field is varying either parallel or perpendicular. So next, these three geometries: spherical geometry, planar geometry, and cylindrical geometry. Only these three geometries are possible whether we are having some Gauss law application. So we will only form these three symmetries: spherical, planar, or cylindrical. Yes. Now we are coming to the calculation part of this Gauss law, which is the important with the view of the exam. So a charge Q is uniformly distributed through a sphere of radius R. What is the electric field as a function of R? Find electric field E at R1 and R2. So this is your R1. So here is a point, and this is your R2. So here is another point, and the radius of this sphere is R, and we have to calculate the electric field as a function of R, and we have given that there is a charge capital Q which is uniformly distributed through the sphere. So what we will do, we will make a symmetry, use some symmetry. So for a sphere, now you guys know that we can form spherical symmetry. So for this point, we will form a sphere which is spherical symmetry. For this point 2, for this R2 2, we will again form a symmetry, and now we can solve. For this bigger sphere, what is the enclosed charge? Obviously Q. What is the flux to the surface? Phi, which is E dot dA, which is into A, which is E into 4 pi r square, because this sphere having the radius small r. So applying Gauss law, we are getting Q upon epsilon naught equals to E 4 pi r square, and hence we are getting ER equals to 1 upon 4 pi epsilon naught Q over r square in the direction of r cap. In the direction of r cap. This r cap is representing the direction. So for the inner one, for this sphere, the inner one sphere, what we will do, we will have some volume ratio, which by which we will conclude this Q enclosed, because that Q, capital Q, was inside this whole sphere, and we are now considering the small part from that bigger sphere. So the Q enclosed will be the aspect of volume ratio. So we can conclude by this formula. Remember this formula in always in your mind. And again we will get flux, and then electric field will be a Q over 4 pi epsilon naught RQ R R cap. R cap is direction. Okay. So if we are putting both these results into a graph, the graph will be between electric field and radius. So there was a question in the exam of NET, and four options were given with different graphs, and we have to tick the right option of the graph, which the question was the variation of electric field with the radius of r having a sphere enclosed with a charge q. So the right graph will be like this: a straight line till A, and then a slope to infinity. So this is the graph for a sphere, and we will have some specific results if we have a point outside the sphere and having that r is greater than r. So what we will do, we can again integrate by volume ratio, but the easy way is to make a Gaussian surface, a Gaussian uh, shell, and then to calculate which is more easy. The next problem is of infinite charged plane. There is an infinite charged plane having the surface charge density sigma, and we have to calculate electric field at distance z above the plane. So if this is x, this is your y, then the z will be upside down. So this z is above the plane or down to the plane. Down to the plane will be minus z, above the plane will be plus z. So the electric field will be either sigma greater than 0 or either for sigma less than 0. So we will again make some symmetry. So I have told you guys that for a plane or for a sheet, we will make pillbox. So what is that pillbox? Pillbox is the shape, is a conventional shape which we make for a plane for solving the problems in a plane, and pillbox is used to be uh, going through this surface. like this pillbox is half up to this surface and half down to this surface. So this pillbox is just piercing this surface, and we are just having our point into this pillbox. So always remember, for plane or sheet problems, we will consider a closed surface that will be a Gaussian pillbox. The pillbox have the symmetry of a cube or cuboid. Okay, cuboid we can say. So let the area of top and bottom be A. We are considering area as capital A. So total charge will be A into sigma. Okay, and outward flux through the top, through this top. Okay, the flux coming out from the top. Sorry, through the top will be EA, and through the bottom will be EA. So the next is through the side we can consider. So outward flux through the sides will be E into area into cos into angle. So what is the angle? You can see that electric field is upside down, and we are having the side like this. So this and this will make an angle of 90 degrees. So obviously cos will be 90. So we are getting outward flux through the sides equal to 0. What we will do? We will total all these flux from upside, from down to the bottom, and from sides, and we are having the total flux 2EA. So now what we will do? We will just apply Gauss law, so that both are the flux. This A sigma upon epsilon naught is also flux, 2EA is also flux. So by calculating this, we are having E equals to sigma over 2 epsilon naught. Okay, so this is for infinite charge plane. Okay, next we are coming towards electric dipole. So first, now you guys know that what is electric dipole. We have discussed in previous class too. In this class, we will have some applications of electric dipoles, and we will do we will see some formulas how to solve the problems of electric dipole in external electric field. So basically, electric dipole is a system consisting two charges, plus and minus, equal in magnitude but opposite in sign, separated by a fixed distance, small distance d, we can say. So the electric field we will derive using Coulomb's law, because electric dipole is not a closed system, so we can't apply Gauss law here. So using Coulomb's law, we will have electric field E equals to 1 upon 4 pi epsilon naught QD over RQ. And this electric field depends on this Q into D. And what is this Q into D? This is our dipole moment, which we also write as P. Okay, so we write P equals to Q into D as our dipole moment in electrostate. Okay, so you know this thing. So if Q and D are those parameters that characterize the dipole, so we are defining P as Q into D. And now, do you guys know that what will be direction of any electric dipole? What is the conventional direction of any electric dipole? Do you know that thing? Anyone can tell me that what is the conventional direction of any electric dipole? कोई भी, anyone, जिसको कोई आइडिया हो कि जिन्होंने पढ़ा हो कि इलेक्ट्रिक डाइपोल की एक स्पेसिफिक डायरेक्शन होती है, सो व्हाट इज दैट डायरेक्शन?
It is always minus to plus.
Yes, you are right. It is always minus to plus. So it is also shown in this picture. There is no need to confusion. So the direction of electric dipole is always from minus to plus. This will also help you while you will solve the problems, because please don't confuse, because always the electric field is towards minus. The flow of electric field we will consider in electrostate as from plus to minus, but while we will use electric dipole, we will do just opposite. We will consider the direction from minus to plus. So please don't confuse. Okay, so this is our electric dipole, and a dipole in a uniform electric field experiences no net force but a torque. What is a torque? Okay, have you guys listened about the force in electrostatic field? The force is like Coulomb force we are considering, but the electric dipole is a system of two charges. And we know that electric dipole has the infinitesimal small distance. Okay, very small distance, not considerable. Sometimes we will just neglect that distance between those two charges, and we consider those charges as one dipole, as one system. So it will never feel any force, it will only experience a torque. What is a torque? Torque is the uh, force. Torque is a type of force which is applied for rotating bodies. Like we are having a system of electric dipole, an electric dipole here, which is oriented, or we can say inclined with angle theta with this electric field E, and this dipole having dipole moment P, the conventional direction is from minus to plus. So if we want to calculate the force, so the force on plus Q charge, F plus will be towards this direction, and the force on minus Q charge will be towards this direction. These two having the same magnitude, plus Q and minus Q having the same magnitude. We can say if this is 5 Coulomb, then this 5q is also, this plus q is also 5 coulomb. So plus 5 coulomb minus 5 coulomb will have the same portion of forces, and having the opposite directions, they will cancel out each other. So we will get no net force for electric dipole. So obviously F will be equal to F plus F minus, which is equals to 0. So what we will do? We will now wanted to calculate some torque. So we will choose a midpoint. Okay. So with a midpoint, by watching this midpoint, we will have some calculate some directions or some distances, like this will be half d sine theta for this one, this will be half d sine theta, this distance will be half d sine theta, this distance will be half d sine theta, and we will just draw a line through this midpoint. Okay, and we will calculate the torque, so that we can find summation of tau equals to tau plus tau minus torque for plus charge and torque for minus charge. So we are getting these types of results, and hence the final result is qd is sine theta. Okay, so we are getting sine theta now. Sine theta means cross product, so it will be q cross de. Sorry, it will be qd cross e. So what is this qd? Qd is the dipole moment, so we can write it as tau equals to p cross e. Okay, so so the unit of torque is Newton meter. Okay, Newton meter, not a joule. Okay, because this torque will not have the dimension of energy. So you guys will remember that the torque has the unit of Newton into meter, and the torque's magnitude is p sine theta, and the direction. So what will be the direction of the torque? We can calculate the direction of torque by right hand rule. What is the right hand rule? We will study in our magnetostatic part, because there the rule will be more important to derive the values of forces in magnetic field. Okay. So can we calculate the energy of an electric dipole situated in an external electric field? We have calculated torque. We know that there is no net force. So the next is we will calculate energy of an electric dipole in an external field. So what will be the energy? Okay, there is a torque, or we can say a type of force which is trying to align this dipole. You can see that this dipole is inclined over this electric field by the angle theta. This is the angle theta. If we want to align this dipole and we want to put symmetrically on this line over here, so what we are getting, we will have this dipole in this orientation at last. So what we will do, we will apply some force, we will do some work. So uh, we are doing some work opposite to the electric field, and that work will be converted as the energy of that dipole. So if the dipole is free to rotate, we will rotate that dipole, and the total work doing so will be W equals to minus PE cos theta initial, means initially the theta, we will put the value of that, and minus cos theta final. When we have rotated the dipole, then we will again get some theta, so that will be theta final. And this minus will be because the work is in opposite direction to the electric field. We are doing some work not in the direction of electric field. That is why we are getting this minus sign. And this work will depend only on initial and final coordinate. Okay, not on many factors, just initial and final coordinates. So if we have a dipole and we are getting some conservative force on it, so we will also define potential energy associated with the dipole. So we have this work W equals to minus P cos theta initial minus cos theta final. So the potential energy of that dipole will be U dipole equals to minus PE cos theta. Not initial, neither final. That will be the resultant of both, and that will be U dipole equals to minus PE cos theta. These are some specific results you guys should always remember and keep in mind while solving the questions related to the dipole. So the U dipole is minus PE cos theta. If now you can see the orientation is like the theta is 90 degree. You can see here we have rotated this dipole and it is now aligned perpendicular to the electric field lines. So we are having theta equals to 90 degree here. So if we are putting theta equals to 90 degree, what we are getting? We are getting U dipole equals to minus PE. Okay, so basically the potential energy of dipole is the cos 90 equals to 0. So we are getting U dipole equals to 0. So basically the potential energy is also depending on the orientation. Okay, we have minimum potential energy and we have maximum potential energy too, but whether we are getting this zero potential energy na, that doesn't mean that we have the zero as a minimum potential energy. The potential energy can also be in minus, and that will be the minimum potential energy. So for different values, we can find different potential energy, like for cos theta equals to minus 1, whether theta equals to pi, we will have, if cos theta equals to minus 1, then we will have U dipole equals to PE. Okay, so that will be the maximum value. And if we have theta equals to 0, So we will have cos theta equals to plus 1. So we will get U dipole equals to minus PE, which is the minimum potential energy. Okay. So basically we have defined three cases of this potential energy in a dipole of a dipole. So potential energy is 0 when theta equals to pi by 2. It is maximum when theta equals to pi. So whether the potential energy is maximum, that is the point of unstable equilibrium. That means on that point of theta, on that orientation of theta, the dipole is not in equilibrium. It is not stable. It will again come into its equilibrium state. So if theta equals to pi, we are having a point of unstable equilibrium. If theta equals to 0 degree, we will have a point of stable equilibrium. That means the dipole will always remain in that orientation, whether we will not force it to change. So basically, uh, we will small summarize this potential energy, and it is better to express the dipole potential energy as U dipole equals to minus P dot D, P dot E, and this dot product will be for cos theta, and theta will decide the value of that potential energy of electric dipole, whether it will be minimum or maximum. Okay, so what we have studied till now, we have studied torque, which is P cross E, PE sine theta. The maximum torque is PE. The unit is Newton meter. The potential energy of dipole, potential of dipole, U dipole, minus P dot E, which is minus PE cos theta. Maximum U max equals to PE. And units are Newton meter again. So, these,
Excuse me, ma'am.
yes, yes.
Ma'am, in this slide, when you sorry, say okay, get it. Now I thought sorry.
Oh, there was any confusion?
Yeah, ma'am. Actually, I thought it was tau in both side, है ना? But in the second equation here is u max. I thought it is
Yes.
again tau. So
No,
now
no,
it's
no.
clear. Thank you, ma'am.
Okay, okay. So these are some specific results we will use in our questions. We will do many more questions of dipoles of different types of questions. I will give you a formula sheet. There in that sheet there will be only formulas of the electrostate what we have studied till now in our two lectures, the last lecture and of the first lecture. There are many types of formulas, and I will give you that formula sheet, or I will give you in the next lecture. In one slide I will add one slide of that formula sheet, so that what you guys will do, you will just remember those formulas on your fingertips. If you can remember all those formulas of the dipoles, of the electric field for any sphere, potential for any cube, potential for a point charge, electric field for a conventional charge, if you can keep remember all these formulas, then you can solve any type of problem of electrostate. So soon I will provide you a formula sheet, so that it will be easy for you guys to solve the questions. So here are some questions we will solve in our lecture. So the question one is, four equal point charges are kept fixed at the four vertices of a square. How many neutral points will be found inside the square? The neutral point means the point where electric field is zero. What is a neutral point? A neutral point is a point in a symmetry where the electric field is zero. So we have four equal point charges. We will put them into four vertices of a square. Let me make some. This is a square, and we will put four charges, one here and again one here. All the four charges are same in magnitude, equal point charges are those, and we have to calculate the those points on which the electric field is 0. So this question is from NET June 2011. So what are those points where the electric field will be 0? Obviously, you can say a center point. On center, there will be always electric field 0. So one point is this, and 4 points are these vertices. On these vertices also, electric field can vanish, or we can say, if I will put one point here, then electric field due to this charge in this direction, electric field due to this charge in this direction, again electric field due to this charge in this direction, again electric field due to this charge in this direction, and all these 4 will cancel out each other, and we will get again electric field 0. So the 4 for these 4 vertices and 1 for the center. So we will have 5 neutral points. Okay, so 5 neutral points. Correct answer is C. Second one is charges Q and minus 2Q are placed on the vertices of an equilateral triangle ABC of sides of length A as shown in the figure. The dipole moment of this configuration of charges irrespective of the origin of choice of origin is. Okay, nice question. This question is from NET December 2011, and these types of questions repeat if they are asking the net dipole moment for any system. They are repeating these types of questions. Sometimes they are putting any square, sometimes they are putting any triangle, sometimes they are putting any pentagon, and sometimes they are putting any hexagon, and so on. And they ask the same thing, the dipole moment of that configuration. And just by changing the values of q, these q, we can have different results. So how to solve these types of questions? I will tell you the easiest method that you should consider whether solving these types of questions in your exams. So this is the symmetry. First thing what you will do, you will choose your arbitrary origin. In the question, a line is given irrespective of the choice of origin is, like they are not giving any condition to choose a origin. That means we are free to choose a origin. So we can choose any origin we want. So just choose a origin between two similar charges. Here are this plus q and plus q2 charges. So I am choosing this point as my origin. Just look carefully. I am choosing this point as my origin. If this side having whole length a, so I will get this as a by 2. Okay, this will be a by 2. Again this will be a by 2, a by 2, half, and I am choosing a origin, let us say ABC. So we are having this point as D, we have this point as C. Okay, so I am choosing D point as my origin. What I will do, if this point is just mid between these two charges Q and Q, so I can conventionally conclude that on this point the magnitude of charges is same. So plus Q and plus Q will add up, and on this D point I have plus 2Q charge. Okay, so this is the diagram which we have made. This is plus 2q. The distance was a by 2. This was a, and here was minus 2q. So we will just find out this distance. What is this? By using Pythagoras rule, you can calculate. This will be under root 3a by 2. Distance from minus 2q to plus 2q. So we are having the distance d. We have to find out the dipole moment p. So what is p? P equals to q dot d. What is q? Q is 2q. We know the magnitude is same 2q. We will not consider sign. And the d is we have calculated. This is under root 3a by 2. We have calculated the distance between these two q's. So this 2 will cancel out this 2, and what we will get? We will get q under root 3a. So we are having the results under root 3a q. Okay, so now we have to consider the direction too. So the conventional direction we use from minus to plus. Because of this conventional direction, just because of this conventional direction, I am putting a minus here. Or we can say that here was j cap na, this side was j cap. So what we are doing, we are coming down toward this j cap. So if I will not apply this minus, then how can I write this answer? I can write this answer as under root 3 a q and minus j cap, and I will put a minus j cap in the bracket. So what will be the answer? The option will be C. Okay. So this is the easiest method. You can solve these types of questions. Next question is, three charges are located on the circumference of a circle of radius r as shown in the figure below. The two charges Q subtended an angle 90 at the center of circle. The charge Q is symmetrically placed with respect to the charge capital Q. If the electric field at center of circle is 0, what is the magnitude of capital Q? So this is the diagram. This is a sphere having radius capital R, and there is an electric field due to charge small q, and we have to calculate the relation between this capital Q and this small q. So how can we do that? There are two methods to solve these types of questions. First method is calculate the forces for all the charges, like force for this q, force on this q, and force on this q. Then you can calculate E equals to force, whether we know the force, what we will do to calculate electric field. Electric field is used to be force upon Q, force upon that charge. So calculate that electric field and then you can find the value. And the second method is this. We can use the Coulomb's law for a point charge, that is E equals to kq over r square. So this E1 is for up direction. This E2 has the angle 45 with this capital Q. This E3 has the same angle 45 with this capital Q. And this is E2 and this is your E3. So E2 and E3 both have the same electric field. So we can calculate here and we will apply this sine theta and we can solve. So we will get Q equals to small q over under root 2. This is the use of Coulomb's law. So this is an easy question and I know you guys can do it. Next question is, consider a hollow charged shell of inner radius A and outer radius P. The volume charge density is rho r equals to k or r square, where k is a constant. In the region A is less than r, which is less than b, the magnitude of electric field produced at distance r greater than a is. Important question, and direct question is asked, not any trick, nothing. So directly we will solve. We have given this rho as k upon r square and we have given the area. Area is specified, the r is greater than small a and less than small b. So this is our Gaussian surface, where over r is up to this, which is greater than this a and small than this b. So we will do our work only in this region. We will apply Gauss law. Charge enclosed by Gaussian surface. What is charge enclosed by Gaussian surface? That is Q enclosed equals to, if we have volume charge density, then rho into volume. So rho is k upon r square and the surface volume for this sphere is used to be 4 pi r square dr. So we can have 4 pi k r minus a. We will put this q in this formula. We are putting this and we are getting the value for a less than r less than b, which is that. Okay. For r greater than b, if r is greater than b, then this our conventional Gaussian surface will be out of this bigger sphere. So now the charge enclosed by the Gaussian surface will be the whole charge enclosed in this symmetry. So the integral will now be from A to B, the whole surface. So this will come as a result of B minus A, and the answer is now changed. So for R greater than B, we will have this electric field. So the correct option will be C for this question. This was a direct question, and using this process, we can solve many types of symmetries. We have here solved the spherical symmetry. We can also solve the pillbox type of symmetries. We can also solve the cylindrical symmetries that are even easier. Those symmetries are even easier. So this was all for today. Any query? If there is any query, you can ask me, or now start studying electrostate so that you can ask some questions. You can put your queries or questions into that WhatsApp group. So your queries are invited. Keep studying and thank you.